Current electricity. In current electricity, today's chapter is Kirchhoff's laws. Kirchhoff's laws. Here we learn what is internal resistance, what is EMF, what is terminal voltage, what are Kirchhoff's laws, how to explain them, how to use them, the principle of Wheatstone's bridge, and its. Let us try to understand the current that is driven by a cell or a battery. When a battery is connected to an external resistance capital R, an internal resistance small r will be developed. A small internal resistance will be developed inside the cell. Inside the cell, a small resistance will be developed. So, the total circuit resistance becomes R plus R, capital R plus small r. If EMF of the cell is say E, capital E, that is say EMF, then the current in the circuit is EMF divided by total resistance, E by R plus R. The current flow will be obstructed by both the resistances, external as well as internal. Hence, the total resistance offered by the circuit is R plus R. So, the current I is equal to E by R plus R. A small amount of potential drop, I small r, a small amount of potential drop, I small r, is established across the internal resistance, and a large potential difference, I capital R, V is equal to I capital R, V across capital R. A large voltage V that is equal to IR across capital resistance, external resistance. So, the voltage across, the potential difference across the ends of the terminals will be reduced by an amount I small r. That is the amount of voltage lost across the internal resistance. It is called loss volts, or potential drop across the internal resistance. So, the available potential difference for the external circuit is only I capital R. So, the EMF minus the potential drop across the internal resistance, that is known as terminal voltage of the cell or battery. Terminal voltage means the voltage, the potential difference that is available for the external circuit, that is terminal voltage, that is equal to EMF of the cell minus potential drop across internal resistance. This is the voltage that is useful. So, that is known as terminal voltage. The terminal voltage will be less than the internal resistance when we draw current from a cell or a battery. Internal resistance. To study the internal resistance, let us select two metallic plates placed in an electrolyte which constitutes a cell. Originally, cells were developed with electrolytes and some plates, metallic plates placed in electrolytes. If we consider such a device, when the current is drawn from such a device, then a resistance is offered by the electrolyte. A resistance is offered by the electrolyte, that is solution in the battery, in the cell. In between the anode and the cathode of the cell, the electrolyte in between the cathode and anode, it offered a resistance that is called internal resistance. The internal resistance depends on the distance between the plates, the area of the plates, the strength of the electrolyte, and the temperature of the electrolyte. These are the factors on which the internal resistance depends. By practical examination, it is noticed that the internal resistance is dependent on the distance between the plates, the area of the plates, the strength of the electrolyte, and temperature of the electrolyte. And it is noticed that the internal resistance decreases with the temperature, increase in temperature. The internal resistance increases with the prolonged use of a cell. If we use a cell for a long time, it is noticed that its internal resistance increases. So, internal resistance is not a constant. It depends on several factors. The internal resistance of a cell can be measured using a potentiometer. We can measure the internal resistance using a potentiometer. EMF of a cell. To understand the concept of EMF, let us consider a cell. Let us notice the high potential terminal is at the left and the low potential terminal is at the right. Short one is low potential terminal and long one is high potential terminal. When it is connected across an external resistance capital R, the ends of the external resistance say P, Q, then a high potential is established at the end P and a low potential is established at the end Q. Across this external resistance, a high resistance is created at P and a high potential is created at P and low potential is created at Q. So the cell sends conventionally the cell's charge from the positive terminal through the resistance to the negative terminal. This is the conventional direction in which we imagine that the charge is flowing. It is shown by the direction of I, current direction. Conventionally, we imagine that the charge is flowing from positive terminal of the cell through the external resistance to the negative terminal. Inside the cell, the charge imagined to be flowing from negative terminal to positive terminal. That is flow inside and outside. Outside is shown by red arrow and inside is shown by green arrow. This is how charge flows through the circuit. And this charge is established, the charge flow is established by the cell. It is by chemical reaction. By chemical reaction, potential difference is created. Because of potential difference, charge flows in the circuit. We imagine this is the way in which the charge flows in a cell. When a charge flows through the external resistance, work is done. The total amount of work done for the flow of charge across the external resistance as well as the internal resistance, that is the closed circuit. So the charge, unit of positive charge starting from the positive terminal, if it flows through the external resistance R and through the internal resistance and comes to the terminal, positive terminal, then it has traveled the entire path, closed path. The work done for the flow of unit positive charge through this closed circuit is termed as EMF of the cell. EMF of the cell is the total work done for the flow of unit positive charge through the entire closed circuit. We define this as the potential difference between the terminals of a cell when the cell is not in use. This is how we define. The potential difference between the terminals of a cell when it is not in use is termed as EMF. And the potential difference when it is in closed circuit, that is called as PD of the cell. Terminal voltage. To understand this concept of terminal voltage, let us take a cell. And by connecting a voltmeter, let us measure the EMF of the potential difference of the cell. That potential difference is called EMF of the cell. If you take a cell and measure the potential difference across its ends by using a voltmeter, it is called the EMF of the cell. But if we connect an external resistance capital R across the cell as shown in the bottom diagram, then a small resistance is established inside the cell, that is internal resistance. I have shown the internal resistance in series with the cell. Then potential difference will be created across the internal resistance and across the external resistance. If I is the current in the circuit, then potential drop across the external resistance is I capital R. Potential drop across the external resistance is I capital R. potential drop across the internal resistance is I small r. Let us measure the potential difference across capital R and small r using the voltmeter and also across the terminals of the cell. The voltage shown by the voltmeter across the terminals of the cell is known as terminal voltage. In this case, the potential difference shown by voltmeter across the terminals is known as terminal voltage. And the voltage shown across the ends of the resistance is potential difference, potential drop across the external resistance. And the voltage shown across the internal resistance is known as potential voltage drop across internal resistance. This we cannot measure, though I have shown it as though it is measured by a voltmeter, but it cannot be measured directly. It can be measured only with the different experiments. So this is the terminal voltage. The terminal voltage will be less than the EMF of the cell because a small potential drop is lost across internal resistance. So terminal voltage V is equal to E minus IR. E is EMF, IR is potential drop across internal resistance. Kirchhoff's law, first law, or current law, or junction theorem. Kirchhoff's first law, or current law, or junction theorem. It is stated as the algebraic sum of the currents is 0 at a junction. The statement is the algebraic sum of the currents is 0 at a junction. To understand this, let us consider a point O as a junction at which several currents are flowing. Here I have taken 5 currents, I1, I2, I3, I4, I5. If we carefully observe, some currents are flowing into the junction and some currents are flowing out of the junction. I1 is flowing out of the junction, I2 is flowing out of the junction, I3 into the junction, I4 out of the junction, and I5 into the junction. Let us take a convention, sign convention. The currents entering the junction are taken as a positive and the currents leaving the junction are taken as negative. Currents entering are taken as positive and currents leaving are taken as negative. I1 is negative, I2 is negative, I3 is positive, I4 is negative, I5 is positive. So the algebraic sum of the currents is minus I1 minus I2 plus I3 minus I4 plus I5 is equal to 0. Algebraic sum of the currents is minus I1 minus I2 plus I3 minus I4 plus I5 is equal to 0. This law states conservation of charge. That means charge is conserved. Charge is neither created at the junction nor destroyed at the junction. There will be no accumulation of charge at the junction. So the total charge that is entering this junction will leave the junction. That is known as the conservation law of charge. Let us take an example. Here I have shown several branches. I didn't draw the devices, but I have shown only the paths and the currents. 2A, 3A, 2A are entering the junction, the first junction. So the total current at the first junction is 7A. Then the current is flowing as 4A is flowing out of the junction and 1A is entering the junction. So the total current that enters the second junction is 7 plus 1, 8. And the current that leaves it is 4A. So the net current through the remaining branch is, which is shown by question mark, is 4A. Because 8A is coming and 4A is flowing out, so another 4A should flow out of this circuit. So this can also be stated as, the Kirchhoff's first law can also be stated as the sum of the currents entering the junction will be equal to the sum of the currents leaving the junction. So we get the principle, sum of the currents entering the junction is equal to sum of the currents leaving the junction. Kirchhoff's second law or loop theorem or voltage law. Kirchhoff's second law or loop theorem or voltage law. It is stated as, in a closed circuit, the algebraic sum of the EMFs and potential differences is 0. The algebraic sum of EMFs and potential differences is 0 in a closed circuit. This is how we state the principle. To analyze this statement theorem, let us take a circuit. In the circuit shown, V1, V2, V3 are three cells with EMFs V1, V2, V3, and R1, R2 are two resistances. All of them are grouped in a loop. Now let us imagine, let us suppose that the current is flowing in the anti-clockwise direction. Current is flowing in the anti-clockwise direction. That is the direction of current flow shown in the figure. Now let us take a sign convention. While using the values of EMFs and potential differences, we use certain sign convention. To take these values, we imagine that we will be traveling along this circuit, moving along this circuit in one direction, either in anti-clockwise direction or in clockwise direction. Suppose if you are moving in the circuit in the anti-clockwise direction, then we will go like this. IR1 is potential difference across R1, V2 is the voltage, and IR2 is the potential drop across R2, and V3 is the EMF, and then V1. That is the direction in which we traverse the circuit in anti-clockwise direction. If you traverse the circuit in clockwise direction, we have to imagine like this: V1, V3, IR2, V2, IR1. That is clockwise direction. So we can imagine to be moving either in the anti-clockwise direction or in the clockwise direction. You have to take only one direction. Remember that you have to take only one direction. While moving so, while imagining as though we are moving in the circuit, we consider the PDs and EMFs to be positive in one direction and negative in another direction. Let us use the following sign convention. Let us take the resistance shown in the middle. In the resistance, the current is from left to right. So in the direction of the current, if you are imagined to be traversing, then take IR as positive. IR is shown positive from left to right, and IR is taken as negative from right to left. That is opposite to the direction of current. While you imagine that you are traversing the circuit in one direction, if the current is in that direction, then take IR as positive. The potential drop across IR1 becomes positive if you traverse the circuit in the anti-clockwise direction. That is the direction in which current is flowing. So in the anti-clockwise direction, IR1 is positive and IR2 is positive. In the clockwise direction, IR1 is negative and IR2 is negative. Let us come to the EMFs. The EMFs will be considered positive if you traverse the circuit from positive terminal to the negative terminal. The EMF will be taken as positive if you cross the cell from positive direction to negative direction. If you cross the cell from negative to positive, then the EMF should be taken as negative. That is the sign convention for EMF. Like this, we adopt a sign convention and then we write the algebraic values of EMFs and potential differences. For example, if you are traversing the above circuit in the anti-clockwise direction, then V1 is negative, V2 is positive, V3 is negative. Once again, if you imagine that you are traversing the circuit in the anti-clockwise direction, V1 is negative, V2 is positive, and V3 is negative. If you imagine that you are traversing the circuit in the clockwise direction, then V1 is positive, V3 is positive, and V2 is negative. So first, memorize this concept and application. Memorize this application. Take several circuits and draw different loops and imagine as though you are traversing the circuit and identify the sign that is to be given to an EMF and to a potential difference. Then, if you imagine that you are traversing the circuit in the anti-clockwise direction in the above circuit, now I am taking anti-clockwise direction rotation. Then IR1 is positive, V2 is positive, IR2 is positive, V3 is negative, V1 is negative. So the algebraic sum of the EMFs and potential differences should be written as IR1 plus V2 plus IR2 minus V3 minus V1 is equal to 0. So I have applied the sign convention and I have written this relation. So this is how we write the Kirchhoff's second law, apply the Kirchhoff's second law. This Kirchhoff's second law states conservation law of energy. Wheatstone's bridge. Wheatstone's bridge consists of 4 resistances. Here in the figure I have taken the 4 resistances as P, Q, R, S. The 4 resistances in the Wheatstone's bridge are P, Q, R, S. They will be connected in series as a loop, as a diamond, in the shape of a diamond as shown in the figure. So 4 junctions will be formed. They are named as A, B, C, D. The 4 resistances are grouped in a loop forming 4 junctions. The 4 resistances are PQRS and the 4 junctions are A, B, C, D. A, C are one pair of opposite junctions. BD is another pair of opposite junctions. AC and BD are opposite sections, 2 pairs of opposite junctions. Battery of EMF V is connected across the opposite junctions AC, and galvanometer is connected across the other pair of opposite junctions BD. Galvanometer is connected across the junctions BD and cell or battery is connected across the junctions AC. AC, one pair of opposite junctions, BD, the other pair of opposite junctions. Let us suppose the current drawn from this battery is say I. Current drawn from the battery is say I. Then this current, it will be divided at A into 2 branches, I1 and I2. I1 flows through P and I2 flows through R. I1, after coming to the terminal B, junction B, once again it will be divided into 2 branches, I3 and IG. I3 flows through Q and comes to C. IG flows through the galvanometer and comes to the terminal D, the junction D. I2 and IG, they join and become I4 and flow through the S. I2 and IG, they join at the junction D and flow as I4 in S. I3 and I4, I3 passes through Q, I4 passes through S, and they join at C, and once again they become I and flow to the battery. This is how the current flow takes place. Now, Let us take the potential differences. Potential difference across P is I1P, across Q is equal to I3Q. Simply apply Ohm's law. Ohm's law is V is equal to IR. So here resistance is P, current is I1. So I1P is potential difference across AB. And I3Q is the potential difference across BC or across Q. I2R is the potential difference across AD. I4S, potential difference across DC. IgG is the potential difference across BD. Now let us apply Kirchhoff's first law and second law. First let us take the first law. From Kirchhoff's first law, the algebraic sum of the currents at a junction is 0. Let us apply this relation to the junction A. We will get I1, I minus I1 minus I2 is equal to 0. We get the relation I minus I1 minus I2 is equal to 0, or I is equal to I1 plus I2. At B, we will get the relation I1 is equal to I2 plus I3 plus Ig. I1 is equal to I3 plus Ig. At B, I1 is equal to I3 plus Ig. At D, I2 plus Ig is equal to I4. At D, I2 plus Ig is equal to I4. At C, I3 plus I4 is equal to I. So these are the relations that we will get for currents applying Kirchhoff's first law. Let us apply Kirchhoff's second law. Let us apply Kirchhoff's second law. Consider the loop A, B, D, A. Take the loop A, B, D, A. In this loop, let us imagine that we are traversing in the clockwise direction. That is A, B, D, A, B, D, A. This is the direction in which we are traversing the circuit. Then, the current is along this direction. So, I1P is positive. IgG is also positive, but I2R is negative. So we will get the relation I1P plus IgG minus I2R is equal to 0. I1P plus IgG minus I2R is equal to 0. Take another loop B, D, C, B. B, D, C, B. In this loop, applying Kirchhoff's second law, we get the relation IgG plus I4S minus I3Q is equal to 0. IgG plus I4S minus I3Q is equal to 0. Let us take another circuit. From the loop A, B, C, V, A. A, B, C, V, A. That is the loop I am considering. In this loop, if we traverse in the clockwise direction, we will get I1P plus I3Q minus V is equal to 0. I1P plus I3Q minus V is equal to 0. Let us take another loop. A, D, C, V, A. A, D, C, V, A. In this loop, in the clockwise direction, we will get I2R plus I4S minus V is equal to 0. I2R plus I4S minus V is equal to 0. And consider another loop. A, B, C, D, A. A, B, C, D, A. In this loop, we will get I1P plus I3Q minus I4S. Derivation of the principle in Wheatstone's bridge. Derivation of the principle in Wheatstone's bridge. The bridge is said to be balanced when the current through the galvanometer is 0. When the current passing through the galvanometer is 0, then we say the bridge is said to be balanced. When the bridge is balanced, the resistances bear a constant ratio. That is known as principle, Wheatstone's bridge principle. Let us derive this relation. If the current Ig is equal to 0, then B and D will be at the same potential. B and D will be at the same potential. So I1 passes directly through Q, so I1 becomes equal to I3. I1 becomes equal to I3 because Ig is equal to 0. Similarly, I2 will be equal to I4 since Ig is equal to 0. These are the relations between currents when the bridge is balanced. Moreover, from Kirchhoff's second law, we will get the relations I1P minus I2R is equal to 0 and I4S minus I3Q is equal to 0. These are the relations which are required. From Kirchhoff's first law relations, we will get I1 is equal to I3, I2 is equal to I4. And from Kirchhoff's second law relations, we will get I1P minus I2R is equal to 0, I4S minus I3Q is equal to 0. Or we can write it as I1P minus I2R is equal to 0 can be written as I1P is equal to I2R. I1P is equal to I2R. And from the relation I4S minus I3Q is equal to 0, we will get I3Q is equal to I4S. These two are equations 1 and 2. I1P is equal to I2R, equation 1. I3Q is equal to I4S, equation 2. From 1 and 2, we can write, dividing 1 with 2, we can write I1P by I3Q is equal to I2R by I4S. I1P divided by I3Q is equal to I2R by I4S. We can cancel I1 with I3 and I2 with I4. Therefore, we get the relation P by Q is equal to R by S. P by Q is equal to R by S. This is known as Wheatstone's bridge principle. P by Q is equal to R by S is the Wheatstone's bridge principle. We can write this relation when the current in the branch BD is equal to 0, Ig is equal to 0. Uses of Wheatstone's bridge principle. We can use Wheatstone's bridge principle to compare two resistances. To compare two resistances, we can use Wheatstone's bridge principle. We can also determine the resistance of an unknown resistance wire using Wheatstone's bridge principle. If there are small strained portions in metals, we can estimate by using a resistance coil called strain gauge. Post office box and meter bridge work on the principle of Wheatstone's bridge. Post office box and meter bridge both are devices which use Wheatstone's bridge principle. Instead of resistances, if we use capacitors, we will get the same principle. Instead of PQRS resistances, if we take the capacitors C1, C2, C3, C4, then the relation obtained is C1 by C3 is equal to C2 by C4. So this relation can be used in capacitors instead of resistances. Summary of this class. When current is drawn from a cell, a resistance acts internally called internal resistance. This internal resistance depends on the area of the plates of the cell and the separation between the plates, the electrolyte solution, etc. And if E is EMF and I is the current drawn from this cell, R is the internal resistance, then E minus IR is called the terminal voltage. E minus IR is terminal voltage. E is EMF, I is current, R is internal resistance. EMF is defined as the work done in moving unit positive charge along the closed circuit, that is known as EMF. Then we will go to Kirchhoff's laws. Kirchhoff's first law or junction law says that the algebraic sum of the currents at a junction is 0. Algebraic sum of the currents is 0 at a junction. That is first law. The second law states that the algebraic sum of EMFs and potential differences is 0 in a closed mesh. In a closed mesh, algebraic sum of EMFs and potential differences is 0. This is second law. Then the relation that is obtained in Wheatstone's bridge is P by Q is equal to R by S. This is Wheatstone's bridge principle. This is the summary of this class.